So we're ready to leave the ideas of this. We'll bring them along where we need them on several occasions in other topics this year in terms of forces and the acceleration that forces cause. But what we've just talked about and seen the example in Newton's cradle is that the idea of momentum is necessary to describe accidents. Momentum is just the mass times the velocity of an object. So somebody like me, if I play football, I have 100 kilograms as my mass. In general, we said the velocity, if you want to be able to relate to that, is generally in the metric system, if it's meters per second, 2.5, 2 1/3 times greater than what the meters per second is in miles an hour. So if I'm a fast runner, I'd say maybe 5 or 6. That is going to be about 15 miles an hour, double plus a little bit more. 4 meters per second is about 10 miles an hour. Okay? 10 meters per second is about 25 miles an hour. So when we're talking, I mean, just as a ballpark, that just gives you an idea in case you get some ridiculously large numbers. But if I'm 100 kilograms and I have a velocity of 5 meters per second, I'm going to have 500 momentum units. Now, unfortunately, like the others, like force as a unit of newtons and length as a unit of meters and mass as a unit of kilograms, is that there is no unit for momentum. And so I end up joking with students and call them momentums. We're going to call it, they have so many momentums. And if you kind of put a word associated with it, maybe you think of it as a group amount. But if I was moving, like I said, 5 meters per second and I've had 100 kilograms, I would have 500 momentums. Now, in a collision, what's important is that the change in your momentum is whatever your final momentum was minus the initial. Okay? So if something hits me, for instance, and I want to know what my change in momentum is, it's whatever I had after the collision, and I subtract the amount of momentum from before. These are vector amounts, and so they do have direction associated with them well. We'll try to keep more simple in the straight line kinds of momentum like we did with motion to begin with. What's interesting is that force does come into play with momentum. Okay, you may see here that says force times time. So if I'm pushing on something for a certain amount of seconds, that force times those seconds will cause a change in momentum. So if I am sitting here, and like I said, I was running at 5 meters per second, I had 500 momentums. If somebody put 100 Newton force on me for 5 seconds in the direction I was running, that would consume all my momentums, and it would stop me. If I ran into something with 500 momentums or a force that was 100 newtons on me in the opposite direction and it went for 5 seconds, that would stop my forward momentum, because the force times time is how much gets changed in the momentum of the object. So those two things can be used. You can take a mass times velocity, what's your final one, and figure out what your mass times velocity initial, and you can then figure out how much momentum is lost. Or you can apply a force on something and for a certain time, and then you can take or add to or subtract from the momentum of your car. You're trying to push your car and you're pushing it in the same direction, you're adding momentum to it. If you're pushing on the other end, you get in front of your car and you're trying to stop it, okay, then you're taking momentum away. So let's do a couple of problems where we can do some momentum. What I'm going to do is just minimize this. Actually, stop those and I'll do a problem as a second